Hello students, welcome to module 28 where we will discuss hypothesis testing on individual coefficients in the multiple linear regression model. So, we are already familiar with the model yi equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui, which is a 3-variable model, the simplest form of the multiple linear regression model. And here we are going to test hypothesis about coefficients like beta 1, beta 2, beta 3 individually. So, we test something about beta 2 using the sampling distribution of beta 2 hat, and we recall from our earlier modules that beta 2 hat follows a normal distribution with mean beta 2 and variance sigma square into 1 upon summation x 2I square into 1 minus r square to 3. So, this is one important information on the basis of which we will test hypothesis about beta 2. Supposing we have the null hypothesis H naught beta 2 is equal to some specified beta 2 naught. So, this is like beta 2 equal to 1, beta 2 naught may have a value 1, the general format is beta 2 naught, and the alternative hypothesis is H1 beta 2 is not equal to beta 2 naught. So, let us see how we go about testing this hypothesis. Now, if the null hypothesis is true, then beta 2 hat will follow a normal with mean beta 2 0. So, that specified value will become beta 2 0, and therefore, from the properties of the normal distribution we can write under H naught, that means if the null is true, beta 2 hat follows normal with mean beta 2 0 and the same variance as we already seen, so that we can convert this to a standard normal variable, that is beta 2 hat minus beta 2 comma 0 divided by sigma square into 1 upon summation x 2I square I 1 minus r square to 3 and whole square. So, that is the square of a standard normal variable. Without the square and with the square root in the denominator, what we have is a normal variable with mean 0 and unit standard deviation. So, if we square the denominator and the numerator, then we have the square of a standard normal variable which is a chi-square with 1 degree of freedom. That is a chi-square with 1 degree of freedom. Another important information that we use is also from this regression, the residual sum of squares divided by sigma square follows a chi-square with n minus 3 degrees of freedom independent of this chi-square 1 above. So, we have two chi-squares, one with degrees of freedom equal to 1, the second one RSS by sigma square with n minus 3 degrees of freedom, and we use a fundamental result that the ratio of two independent chi-squares each divided by its respective degree of freedom gives us an F distribution. So, beta 2 hat minus beta 2 0 square divided by sigma square upon summation x 2I square into 1 minus r square 2 3 that's the chi-square with 1 degree of freedom. This whole thing divided by RSS, the residual sum of squares, by sigma square divided by n minus 3, that is basically chi-square 1 divided by chi-square n minus 3 divided by n minus 3, which gives us the F distribution with degrees of freedom 1 and n minus 3. So, it is with this test statistic that we will test the hypothesis H naught beta 2 equal to 0 against the alternative hypothesis beta 2 not equal to 0, and we will convert it into a t distribution, which makes the test very simple. We will now see how to convert this F statistic into a T statistic. It is a fundamental result that only in case of an F distribution with the numerator having 1 degree of freedom and the denominator general degree of freedom, we can take the square root of this, and that is represented as a T distribution. So, therefore, the square root of this will follow a T distribution with n minus 3 degrees of freedom. So, beta 2 hat minus the specified beta 2 0 and take off the square, and in the denominator what we have is we simplify by striking off this sigma square and this sigma square, and that RSS by n minus 3, what remains here is nothing but sigma square hat. This term sigma hat into this expression, the square has gone away, sigma hat into this expression, this is known as the standard error of beta 2 hat. It is the estimate of the variance and the square root of that. It is the square root of the estimated variance of beta 2 hat. It is the square root of the estimated variance of beta 2 hat, that is called the standard error. So, here we write standard error of beta 2 hat that less than T a by 2 n minus 3 is equal to 1 minus a. It will be very clear once we use this diagram. So, we have two goal posts, and to the right of this goal post the probability is a by 2, or to be more specific we can write 100 into a by 2%. Similarly, to the left of this goal post probability is 100 into a by 2%. So, if a is 5, that means this is 2.5%, this is also 2.5%, and this we denote as T a by 2 comma n minus 3, and because of symmetry of the T distribution we denote this goal post as minus T a by 2 n minus 3. So, what this probability statement says is very simple, that this test statistic will lie between these two goal posts with the probability 1 minus a. This side is a by 2, this side is a by 2. So, this right hand side the shaded area and the left hand side the shaded area, these together contain a, and therefore, the probability that the value will lie between these two goal posts, this is 1 minus a. So, for example, if a is equal to 0.05, that means 5%, then this is the 95%. So, 1 minus 0.05, that is 0.95. So, this is the 95% confidence interval. So, we can say with 95% surety that this test statistic must lie between these two goalposts. But if we observe it to be lying beyond these two goalposts, then we reject the null hypothesis, otherwise we accept it. So, what is the rule? The rule is we reject H naught at the A percent, or actually 100 into A percent, 100 into A percent level of significance if the calculated value of this t, this is a t statistic. So, if the calculated value of t calculated exceeds modulus of t a by 2 n minus 3, that means if it is either greater than this or less than this. So, if it exceeds mod t a by 2 with n minus 3 degrees of freedom. So, the decision rule is we reject the null hypothesis at the specified level of significance if the calculated test statistic exceeds, this is called the critical value, and these regions are called the critical regions. So, if this falls in the critical region, that means if it exceeds the critical value, then we reject the null hypothesis, because this t statistic is based on the null hypothesis. If this is true, then beta 2 hat minus beta 2 comma 0 divided by standard error of beta 2 hat will with 95% confidence lie between these two limits. So, that is very simple, just compute the t statistic and compare it with the critical values. Now, we will go on to some more tests about a single coefficient, but before that please note that because we have two goalposts here, it is called a two-tailed test. Now, let us take a look at one-tailed tests. The null hypothesis is as earlier H naught beta 2 equal to beta 2 naught, but the alternative hypothesis is now beta 2 greater than beta 2 naught. And we know that we will use the test statistic beta 2 hat minus beta 2 0 divided by standard error of beta 2, which follows a t distribution. So, how does this get reflected in the t distribution? From this diagram we see that the probability of the calculated value of the t statistic exceeding this particular value t a with n minus 3 degrees of freedom is only a. So, if a is 0.05, then we can say that the area to the right of this post is 5%, and therefore, in 95 out of 100 cases we will have this value, calculated value of the t statistic, lying to the left of this post. Now, to the left of this post, if we get the calculated value, that means we can say that this, we do not have any reason to reject this, but we will reject the null hypothesis if we get a calculated value which is greater than the critical value t a comma n minus 3 degrees of freedom. So, therefore, the decision rule is reject H naught at the 100 into a minus 100 into a percent level of significance, that means at the specified level of significance, if the calculated value of the t statistic, this is the calculated value of the t statistic, if that exceeds the critical value, which is t a n minus 3 degrees of freedom in this case. Similarly, if the alternative hypothesis had been H1 beta 2 less than beta 2 naught, then we would have taken a look at the other tail, not the right hand tail, but the left hand tail. So, here we can identify the left hand tail as minus of t a n minus 3 degrees of freedom, because the t distribution is symmetric, and therefore, we say that we reject H naught at the specified level of significance if t calculated. Please remember that this t calculated is the same as this, if the calculated value of t is now less than minus t a with n minus 3 degrees of freedom. So, otherwise we accept H naught. So, that gives us a clear idea about how to conduct tests of significance on individual coefficients of the multiple linear regression model. After this, we will take a look at the p-value approach, which is another approach. It is an equivalent approach, seemingly different but equivalent approach to testing of hypothesis. So, now we will take a look at the p-value approach to testing of hypothesis. The p-value approach to testing of hypothesis on individual coefficients is as follows. We already saw that beta 2 hat minus beta 2 0 divided by standard error of beta 2 hat is the calculated value of the t statistic. We denote it as t calculated. This is our familiar t distribution with the appropriate degrees of freedom depending on the number of variables. Say it is n minus 3 with 3 variables, 3 explanatory variables, or 2 explanatory variables and 1 intercept, we have t n minus 3. So, this is the t distribution. Now, we will locate this value on the t distribution, and that is the value of calculated t. To the right of this, say the area is signifying probability 4%. That means that we can safely reject H naught at the 5% or 10% level of significance. Instead of taking a critical value that we had taken earlier, this was the critical value which we had taken earlier, say this was t 0.05 n minus 3 degrees of freedom, and in the earlier approach we said that this dotted area was the critical value. So, calculated t lying to the right of the critical value means we reject H naught. Instead of doing that, we do away with this arbitrary critical value and we simply find out the probability of t being greater than what we have calculated on the basis of this sample. So, the smaller this region is, if it is 4%, then we reject the null hypothesis at the 5% level of significance for a one-tailed test. If it is even smaller, all the more reason to reject H naught. What was H naught? H naught was beta 2 equal to beta 2 0 and H1 was say beta 2 greater than beta 2 0. So, we will reject this if this p value is very small. So, if it is less than 4%, then there is all the more reason that we reject this. So, we can see that although apparently it is an alternative approach, the two approaches are equivalent. So, that, dear students, is the p-value approach to testing of hypothesis. We now summarize what we have gathered so far in terms of the k variable model. So, that is our k variable classical linear regression model. The two-tailed test has the null hypothesis beta 2 equal to beta 2 naught and alternative hypothesis beta 2 not equal to beta 2 naught. And we already know that this is our test statistic beta 2 hat minus beta 2 0 divided by standard error of beta 2 hat. However, one thing needs to be kept in mind, that is the standard error, which is the square root of the estimated variance of beta 2 hat, is now sigma square hat, that is RSS divided by n minus k. Sigma square hat will be RSS divided by n minus k instead of n minus 3, and the pure x2i square will be 1 upon, that is pure x2i square is x2i square, the residual when x2i is regressed on x3, x4 up to xk. That was the concept. So, when x2 is regressed on all other variables x3 up to xk, then the residue that is obtained is pure x2i square. So, that is the difference between the test statistic of the k variable model and that of the 3 variable model. So, this is now the test statistic, the rest is as earlier. We have two goalposts. To the right of this a by 2% or 100 into a by 2%, to the left of this 100 into a by 2%. For example, if it is a 5% level of significance, then this is 2.5%, this is 2.5%. So, we reject the H naught, we reject beta 2 equal to beta 2 naught if our calculated value of the test statistic, that is T calculated, if it either goes to the right of this post or comes to the left of this post, that is it is exceeding the modulus of T a by 2 n minus k. Otherwise, we accept H naught. Similarly, for the one tail test, we use again the same test statistic, only now it is a one tail test. So, we reject H naught if the calculated value of T is to the right of T a with n minus 3 degrees of freedom, because to the right of that the probability is small. So, we should have a value which comes to the left of this. If we go to the right of this, then we have reason to suspect the null hypothesis. Here also, if we are either to the right of this post or to the left of this post, then we have reason to suspect the null hypothesis, which is why we reject H naught. Otherwise, we accept H naught at the appropriate level of significance. Before we end this module, we will take a look at a test which is not very frequently used, but nonetheless it is useful to have a look at the test on sigma square. So, for testing sigma square, we first build the confidence interval for sigma square. We know that RSS by sigma square follows a chi-square with n minus k degrees of freedom, and that gives rise to the probability statement that probability RSS by sigma square lying between these two limits is equal to 1 minus a. Which are these two limits? We draw the chi-square distribution and then we mark out the critical value chi-square a by 2 n minus k degrees of freedom as that value to the right of which the probability is only 100 into a by 2. Similarly, we have another goalpost to the left, but mark that this is not a symmetric distribution. So, we write chi-square 1 minus a by 2 with n minus k degrees of freedom. That means, to the left of this also the probability is 100 into a by 2. And so, with these two goalposts once again, what we can say is we can test sigma square having a particular value sigma square naught against H1 sigma square not having that value. By now, you would have understood that because we have two goalposts is a two-tailed test, and so the alternative hypothesis is not greater than or equal, greater than or less than, it is not equal to. So, what do we make out of this? In 95 out of 100 cases, the value of RSS by sigma square, putting sigma square equal to sigma naught square. So, in 95 out of 100 cases, this value of the test statistic, when we put sigma naught here, it should lie between these two goalposts, and therefore, we will reject H naught if our calculated value does not lie between these two posts. So, simple, the decision rule is we reject H naught at the 100 into a% level of significance if the calculated value, this under H naught, if the calculated value RSS by sigma square hat, that means I am repeating RSS by sigma square, RSS by sigma square, where this sigma square is given this value sigma square naught. So, if this value RSS by sigma square naught, if this does not lie between this interval, then we will reject the null hypothesis, that is we will reject sigma square equal to sigma square naught, otherwise we will accept it. So, this is another example of a two-tailed test which is not used very frequently. Similarly, we can modify it for a one-tailed test. Only thing that we do is we now ignore this, and this will not be a by 2, this will be simply a. So, we will reject it if the calculated value lies to the right of this post. So, with that we come to the end of this module, where we have tested individual coefficients in the multiple linear regression model.